The interconversion of acid derivatives is a reaction that we're going to take a look at next. Now, there's a lot of transformations, but really only one general mechanism. So the reaction can be described as an addition-elimination mechanism. So one flavor of the reactions takes a nucleophile, adds it to the carbon of our carboxylic acid derivative carbonyl. We would then form a tetrahedral intermediate that then undergoes reformation of our carbonyl and the expulsion of our leaving group Y. The other flavor of this reaction takes a nucleophile that has a neutral charge, no charge to it, right? It's neutral. Takes a lone pair, grabs that carbon, leaving group is displaced, and then our nucleophile that has a positive charge is deprotonated to form this neutral final product. Now again, the principle that we're going to see down below here is that the more reactive acid derivatives can react to form the less reactive derivatives. So up at the top of the hill here, we have acid chlorides. Now remember, these are all going to form those tetrahedral intermediates. So upon the collapsing of that intermediate back down to a carbonyl, that chloride is going to be your leaving group. Now remember, weak bases make better leaving groups, generally speaking. And this is true specifically in reactions in which we see one step, like in SN2. It's true also for these reactions. So chloride comes from HCl, which is a strong acid. Right? Anhydrides have this as their leaving group, right? And that is resonance stabilized. So that's a good leaving group. Right, down here, we're going to see that this alkoxide can leave. It's not a great leaving group, but it can leave. So the NH2 minus is a stronger base than an OR minus. So it's a little bit tougher to have that leave. And down at the bottom, you have our carboxylate. So the idea here is that, again, the better leaving group, the faster the reaction. The other thing to consider here, too, is that disrupting the resonance on the acid derivative, so that's this guy here, is unfavorable. So if you look at the acid chloride, that structure has no resonance, right? I mean, it doesn't have any resonance that makes sense. The anhydride does, though, right? So the anhydride has a set of electrons here. They can come up this direction or can come up that direction. Okay. The ester also has resonance too. Comes up like this, right? And the amide also does too, where we have an electron flow that direction. So besides carboxylates, amides have the strongest resonance, then esters, and then anhydrides. And that just fits perfectly into the reactivity sequence that we see listed on the top of this page here. Now, let's take a look at some of these reactions. And you guys are going to see very quickly how similar they are to each other. So we're going to start off here by taking a look at an acid chloride reacting to form an anhydride. An acid chloride has this general structure, and a carboxylic acid, we all know, looks like this. So when this reacts with our acid chloride, it turns out that the carbonyl probably is more nucleophilic than the OH of our carboxylic acid. And so the resulting structure here, kind of turning around that carboxylic acid, looks something like this. So there's your tetrahedral intermediate and your carbonyl with a plus charge. So this intermediate has two additional resonance structures. So we can take a pair of electrons in our pi bond, convert them into a lone pair on that oxygen. That leaves us with a plus charge here. There's an additional resonance structure here where we pull those electrons from our OH down to that carbon. So this leads to our tetrahedral intermediate, and that whole set there is our resonance structures. Once we're here, we go back to eliminating our chloride. That gives us our second to last intermediate. Loss of that chloride gives us our carbonyl back. And in our last step, some type of a base comes over and does a deprotonation to give us our anhydride. So let's look at an acid chloride to an ester. How about C5H11 and then carbonyl Cl. And let's add to that ethanol. So this acid chloride comes from the carboxylic acid C5H11COH. That's caproic acid. So this thing smells like goats. Now, when we react these two things together, we have our oxygen there attacking our carbon, right? So we're going to get another tetrahedral intermediate here. So it'll be our C5H11 carbon. Right now that's an oxygen with a minus charge there. Here's our chloro group, and then we have our OET with an H down here and a plus charge. So you can guess what's going to happen here, right? There's your tetrahedral intermediate again and again. These are very similar reactions, so we're going to come over, kick off the chloride, right? What that's going to give us next here is our C5H11 carbonyl, and then we'll have our oxygen with its lone pair, it's H and it's ethyl and a plus charge there. And then the last step here again is chlorine or pyridine. That can be used too, just like before. And anyway, we do our deprotonation and then voila, that is our product C5H11 carbon O ET here. Now, this smells like strawberries. So you can take something that has a goat-like presence and you can convert it into an ester, which smells, this particular ester smells like strawberries. All right, so I've typed this one out for you because you could probably see and be able to anticipate exactly what's going to happen here. But you have a lone pair, right, coming over, attacking your carbon. Here's your tetrahedral intermediate, and then your deprotonation down here at the end. The only thing down here is that we already have a base present, so we don't use chloride here. Probably use our amine to do that. And then that makes the amide down here at the end, right? So you're making your amide. Now, the next three reactions are also going to follow that same general suit here. So walking through that, here we have our lone pairs of an alcohol attacking the carbon of our anhydride. So what we're going to form here is our R group, our carbonyl, oxygen. That carbon is this carbon here. That's an oxygen with a minus charge on it. Right, we're going to have here an R group And then down here below we have our oxygen with our R prime and our H lone pair and a charge there. So what we're going to do next is we're going to swing down, and again that's your tetrahedral intermediate, right? So we'll label that tetrahedral intermediate. And we're going to have a loss of our leaving group. So we're going to do this. Right? Now what that's going to give us here is our R C double bond O O minus. Right, so that's the left side of this molecule. And then I'm going to kind of rearrange things around a little bit here. So I'm going to move this R group down to this position. That puts my carbonyl just like so, and my O, R prime, H, just like this. And then the last step of that reaction is your deprotonation. So here, you're probably going to end up using for that your R, right, COO minus there. Right, that's what this is, right? So that's going to swing around down here, grab that H, and then there you go. And then that will give you here an ester plus a carboxylic acid. All right. Well, what about the anhydride to an amide? Again, same general reaction that we just saw. So we're going to swing around. We're going to form our oxygen with our minus charge, our R group, your nitrogen with your R prime, your H, and your plus right there. All right, so there's your tetrahedral intermediate again. So same idea, swinging down here, making our carbonyl again, and kicking off, right, our leaving group there. So that'll give us an RCOO minus, and then plus. I'm going to swing that R group down just like we did before. So get you your carbonyl, and then your R prime, H, H plus there. And to do that last deprotonation, we could use our R prime NH2, or we could use RCOO minus. But we're going to come over here and grab one of these H's, and that'll give us our neutral final product, right? So you're going to get an RCOOH if you use that carboxylate, plus your R carbonyl, so your NH R prime. So an ester to an amide, same general principle here. So that's going to give you your R here, right? Your carbon, oxygen, minus charge. Here you have your O R group, and that's going to be connected to a nitrogen with an H, an R prime, and another H, and a positive charge there. Okay, so that's your tetrahedral intermediate again. So there's your Ti. That's going to swing down, and now we're going to kick off this. So it's true you could kick off the nitrogen, but that just takes you back a step in this reversible step here. So let's see what that's going to give us. That's going to give us an R carbonyl. Right, you got your carbonyl there. Let's see, a nitrogen with your R prime and your H and a plus. And then down here, plus RO minus. Now, this is a little different. We haven't seen an alkoxide leave as a leaving group. Now, we said before that in general, this is an unfavorable step if it's an SN2 reaction. So we'll see on the next page that the mechanism is what really decides whether or not this alkoxide can leave. Right, now, the last thing that we do over here is we grab our RO minus, right, or your NH2 here, And anyway, you come over here and you're going to grab a proton to give you your final product. So here you have an ROH plus your R carbonyl, and then your NHR prime down here below. Right? So you get your alcohol plus your amide here.